At the smallest scales imaginable, the world begins to behave in ways that feel unfamiliar. Objects lose their sharp edges. Certainty softens. Events no longer follow a single predictable path. Light arrives as both ripple and packet. Particles exist more as tendencies than as things. What once seemed solid becomes strangely fluid, suspended between possibilities. Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations. And if it's not too much to ask, I'd love to know where you're watching from tonight. Quantum physics did not begin as an attempt to be strange. It emerged because careful measurements refused to agree with familiar rules. Heat behaved oddly. Light arrived in unexpected ways. Matter itself seemed unsure of where it was or how fast it moved. What followed was not a rejection of reality, but a deeper look at it, guided by patience, precision, and a willingness to let go of certainty. Over time, this quiet framework revealed a universe built not from definite outcomes, but from probabilities. A place where events are shaped by chance within firm boundaries, where observation matters, and where the act of looking is itself a form of interaction. The quantum world does not hide behind mystery for its own sake. It simply follows rules that feel unfamiliar to human intuition. Tonight's journey moves gently through that world, not to solve it, and not to force it into neat explanations, but to rest with its strangeness, to explore how reality behaves when certainty loosens, and to notice what it feels like to let questions remain open. Settle in, let the sharp edges soften, and allow the strange, quiet logic of the quantum world to unfold slowly. Quantum physics has a reputation for being strange, confusing, even unsettling. But when approached slowly, it becomes something else entirely. It becomes a story about limits, uncertainty, and the surprisingly gentle rules that govern the smallest pieces of reality. A story that does not demand answers, only attention for as long as it feels comfortable. So as the world outside grows quieter and thoughts begin to soften at the edges, here is a question to carry gently into the night. What if the universe, at its deepest level, is not built from solid things at all, but from possibilities quietly waiting to become real? At the end of the 19th century, physics felt settled in a way that is difficult to recapture now. The universe appeared orderly and cooperative, governed by laws that were not only reliable but reassuringly smooth. Motion followed clean paths. Heat flowed in predictable directions. Light behaved as a wave, spreading gently through space according to equations that had been tested again and again. There was a sense, quietly shared among many physicists, that the great structure of reality had already been uncovered, and that what remained were refinements rather than revelations. This confidence did not arise from complacency. It grew out of extraordinary success. Classical physics explained the workings of engines and bridges, the behaviour of gases, the ticking of clocks, and the motion of planets with remarkable precision. It powered industries, illuminated cities, and gave the impression that nature, once mysterious, had finally agreed to be understood. With enough patience and careful calculation, it seemed that almost any physical question could be answered. Almost. The first sign of trouble did not arrive with a dramatic contradiction or an exotic experiment. It appeared in a place so familiar that it barely raised suspicion at all. It began with warmth. When an object is heated, it begins to glow, at first faintly, then more intensely as the temperature rises. Iron turns red, then orange, then white. Coals brighten, filaments shine. This glow is not decorative. It is radiation, emitted as the vibrating atoms within the object release energy into their surroundings. The relationship between temperature and emitted light was easy to observe and seemed, on the surface, easy to explain. This behaviour was known as blackbody radiation. Classical physics approached the problem with confidence. Heat was energy, and energy was something the equations handled well. As temperature increased, more energy should be available to radiate away. The mathematics suggested that hotter objects would emit more light at higher frequencies, shifting steadily towards shorter wavelengths as the temperature rose. When the calculations were carried through fully, however, the results became impossible to ignore. According to the equations, the energy emitted at very high frequencies should increase without limit. As wavelengths grew shorter and shorter, the predicted radiation surged upward, racing toward infinity. The mathematics did not merely disagree with experiment. It produced results that could not exist in the real world. Infinite energy, not as a poetic exaggeration, but as a literal outcome of the formulas themselves. Nothing in nature behaved this way. No heated object unleashed endless radiation. The equations were internally consistent, yet profoundly wrong in their conclusions. The mismatch was so stark that it earned a blunt name, the ultraviolet catastrophe. Physicists tried to fix it without abandoning familiar ideas. They refined assumptions, adjusted models, and scrutinized experimental setups. But no amount of careful tuning could rescue the predictions. The failure did not come from careless measurement or flawed logic. It came from pushing classical ideas into a regime where they no longer applied. Something about the picture of energy itself was breaking down at very small scales. For a time, this failure lingered as an irritation rather than a crisis. It was uncomfortable, but it was also isolated. The rest of physics worked too well to suggest that the entire framework was in danger. Surely this was a technical problem, solvable with the right mathematical insight. Then Max Planck entered the story. Planck was not a revolutionary by temperament. He was methodical, cautious, and deeply committed to the classical worldview. He did not believe that physics required a fundamental overhaul. His aim was modest and practical. He wanted the equations describing blackbody radiation to match what experiments were clearly showing. Faced with mathematics that refused to behave, Planck made an unusual move. Instead of adjusting the equations further, he adjusted the assumptions beneath them. What if energy could not be exchanged in arbitrary amounts? What if it arrived in discrete steps? Rather than flowing smoothly like water from a tap, energy might be transferred in tiny packets, each with a fixed size. You could add them together, but you could not divide them endlessly. The image was closer to counting coins than measuring liquid. This idea was introduced not as a claim about reality, but as a formal device. Planck treated it as a mathematical convenience, a way to force the equations into agreement with observation. To make the numbers work, he introduced a small constant that set the scale of these packets. Its value was extraordinarily tiny, so small that it seemed unlikely to matter beyond this specific problem. When Planck recalculated the radiation curve using this assumption, the catastrophe disappeared. The predictions aligned with experiment. The runaway energy was gone. The curve bent gently instead of exploding upward. The equations finally matched the real world. Planck had solved the ultraviolet catastrophe. And yet, he did not trust the solution. Planck himself regarded quantization as a temporary patch, not a fundamental truth. He believed that a deeper explanation would eventually restore continuity to physics and render his assumption unnecessary. The universe, he felt, surely did not operate in abrupt, jerky steps. The packets were scaffolding, not structure. From a modern perspective, it is tempting to view this moment as the birth of quantum theory, a dramatic turning point in the history of science. But at the time, it felt far less significant. There were no bold proclamations, no sense that certainty had cracked. There was simply a problem that had been fixed in the most economical way possible. Planck published his result quietly as a careful piece of mathematical work. Others took note, appreciating that the equations now behaved. Few immediately grasped the deeper implications. After all, classical physics still worked beautifully in almost every other context. The interpretation could wait, but the assumption could not be confined to one corner of physics for long. If energy exchange was quantized in heated objects, why not elsewhere? Why should atoms absorb and emit energy smoothly if radiation did not? Why should light interacting with matter respect continuity when heat did not? Gradually, similar patterns began to appear in other experiments, hinting that Planck's reluctant assumption might reflect something real. The failure of classical ideas at small scales was not a failure of intelligence or effort. It was a failure of extrapolation. Concepts shaped by everyday experience had been extended beyond their natural limits. At human scales, energy changes appear smooth because the steps are too small to notice. At very small scales, those steps mattered. The universe, it seemed, was keeping count. This counting did not disrupt daily life. Heat still flowed, light still glowed. The world remained solid and predictable. But beneath that smooth surface, the assumption of infinite divisibility had been quietly set aside. Planck himself remained cautious for years, resisting more radical interpretations. Others would take those steps instead, applying the idea of quantization more broadly and discovering that it fit far more of nature than anyone had expected. At this early moment, though, none of that was obvious. There was only a glow that refused to behave, equations that misbehaved in response, and a careful physicist who adjusted the rules just enough to make sense of the measurements. The first crack in reality did not announce itself loudly. It appeared as a small assumption, tucked into a calculation that erased an impossible result. Physics did not collapse that day, but it did for the first time admit that its smooth picture of the universe had limits. Light has always felt gentle. It fills rooms without asking permission, slips through windows, and quietly makes the world visible. Long before anyone tried to describe it with equations, light was treated as something smooth and continuous, more like a ripple spreading across water than a collection of individual things. By the late 19th century, this intuition had hardened into certainty. Light was understood as a wave, and a remarkably well-behaved one. It bent, it spread, it interfered with itself, and every careful experiment seemed to confirm that picture. Classical physics was very comfortable here. Waves were familiar territory. Water waves, sound waves, vibrations along a string, all behaved in ways that could be captured cleanly by mathematics. Light fit neatly into that family. Its colour depended on frequency. Its brightness depended on intensity. Make the wave taller and the light grows brighter. Change the frequency and the colour shifts. The relationship felt natural, almost obvious. The trouble began when physicists stopped asking how light moved through space and started asking how it interacted with matter. One experiment in particular refused to cooperate no matter how carefully it was performed. It involved shining light onto a metal surface and observing what happened to the electrons inside. Under the right conditions, electrons would be ejected from the metal, springing free as if nudged loose by the incoming light. This became known as the photoelectric effect. At first glance, it seemed straightforward. Light carries energy. Energy transfers to electrons. Electrons escape, increase the brightness of the light, and more energy should be delivered. That expectation turned out to be wrong. What experiments revealed was strangely precise. Below a certain frequency of light, no electrons were emitted at all. It didn't matter how bright the light was. The metal remained unaffected. Turning up the intensity changed nothing. The electron stayed firmly in place. Then, increase the frequency slightly, Even if the light is faint and electrons are released immediately, there is no waiting period, no gradual build-up. The effect either happens at once or it does not happen at all. This behaviour was deeply uncomfortable for the wave picture of light. If energy arrived continuously, dim light should still deliver energy, just more slowly. Given enough time, electrons should eventually absorb enough energy to escape. But time did not help. Brightness did not help. Only frequency mattered. It became clear that brightness and energy were not the same thing. Into this puzzle stepped Albert Einstein. In 1905, Einstein was a young physicist working in a patent office, far from the centres of academic authority. He had been thinking carefully about Max Planck's earlier work on blackbody radiation, and in particular about the strange suggestion that energy might be exchanged in discrete packets. Planck himself had treated that idea cautiously, almost apologetically, but Einstein recognised that it might reach further than anyone expected. What if light itself arrived in packets, not just energy exchanged during heating, but light as it interacted with matter? Instead of a smooth wave delivering energy gradually, light might come in individual bundles, each carrying a fixed amount of energy determined by its frequency. With that shift, the photoelectric effect fell neatly into place. Brightness now controlled how many packets arrived, not how energetic each one was. A bright low-frequency light delivered many packets, but each packet carried too little energy to free an electron. No matter how many arrived, none would succeed. A dim, high-frequency light delivered fewer packets, but each one carried enough energy to do the job. One interaction was enough. The electron did not slowly accumulate energy. It received it all at once or not at all. Einstein referred to these packets as light quanta, a deliberately cautious name that avoided claiming too much. Later, they would be called photons, but even that word can mislead if taken too literally. A photon is not a tiny marble racing through space. It is not a miniature particle in the everyday sense. It is better understood as the smallest possible exchange of light energy, a single, indivisible interaction between light and matter. Light can still spread like a wave while it travels. It can diffract, interfere, and overlap with itself in ways that only waves can. But when it gives up energy, it does so in whole steps. No fractions, no partial exchanges. Once again, the universe reveals a preference for counting. This did not overturn the wave picture of light. Interference patterns still appeared. Diffraction still occurred. The wave description remained essential, but it was no longer sufficient on its own. Light behaved like a wave when it moved through space, and like a collection of packets when it interacted with matter. Both descriptions were necessary, each illuminating a different aspect of the same phenomenon. Einstein's proposal was bold, but it was grounded firmly in experiment. The photoelectric effect behaved exactly as the packet idea predicted, and further tests continued to confirm it. In 1921, Einstein was awarded the Nobel Prize in Physics, not for relativity, but for this explanation of how light ejects electrons from metal surfaces. Light, it turned out, didn't merely flow. It arrived. This distinction quietly reshaped physics. Brightness came to mean quantity. Frequency came to mean capability. One determined how many interactions occurred, the other determined what those interactions could accomplish. Once seen clearly, the difference could not be ignored. In everyday life, nothing seemed to change. Lamps still glowed smoothly. Sunlight still warmed skin. Light still appeared continuous. The packets were too small, the steps too fine, to notice without careful experiments. But beneath that smooth surface, the counting continued. Each interaction between light and matter occurred as a discrete event, precise and indivisible. Each freed electron testified to a simple rule that nature appeared unwilling to bend. Energy arrives in steps, and light, however gently it may appear to flow, keeps track of every one of them. At first glance, the double slit experiment looks almost too simple to matter. A source of light, a barrier with two narrow openings, and a screen placed behind it to catch whatever makes it through. Nothing about the setup suggests that it should unsettle centuries of intuition. It feels more like a tidy classroom demonstration than a moment that would quietly reshape how reality is described. And yet, this modest arrangement turned out to be one of the most revealing experiments ever performed. To understand why, it helps to begin with waves, because waves were exactly what everyone expected to see. When a wave passes through a narrow opening, it spreads out. Water waves do this. Sound waves do it too. Light waves, long understood to behave in the same way, also spread as they pass through gaps. If there are two openings instead of one, the waves emerging from each overlap with one another, sometimes reinforcing each other, sometimes cancelling out. This overlapping produces a pattern of alternating bright and dark regions known as interference. On a screen, it appears as a series of evenly spaced bands, a visual fingerprint that waves leave behind wherever they meet and mix. When light is shone through two narrow slits, this interference pattern is exactly what appears. Not two bright patches behind the slits, but many bands stretching across the screen. The result is so clear and repeatable that it leaves little room for doubt. Light is behaving like a wave. For a while, that seemed to be the end of the story. The puzzle only deepened when physicists asked what would happen if the light were made extremely faint. Instead of a steady beam, imagine sending light toward the slits one photon at a time, with long pauses in between. Each photon arrives alone, with no neighbours close enough to interact with in any ordinary sense. If light were truly behaving as a stream of particles, the expectation would be simple. Each photon would pass through one slit or the other, strike the screen, and leave a single dot. Over time, those dots should form two loose clusters aligned with the slits. That is not what happens. When the experiment is performed this way, the screen does fill with dots, one by one, each arrival separate and unremarkable. But as the dots accumulate, a familiar structure slowly emerges. Bright regions where many dots appear, dark regions where almost none do. The same interference pattern seen with a continuous beam. A wave pattern built patiently out of individual events. This result is difficult to absorb at first. Each photon arrives on its own. There is nothing else present to interfere with, and yet the overall distribution looks exactly as if waves had passed through both slits and overlapped with themselves. Somehow, each photon contributes to a pattern that seems to require the presence of many at once. The natural question follows almost immediately. How does a single photon know where to land? It does not behave like a tiny marble choosing a single path and a single destination. Instead, it behaves as if its behaviour between emission and detection is described by a range of possibilities. The photon does not travel along one definite route in the everyday sense. It evolves in a way that allows many potential outcomes, each with its own likelihood. The interference pattern is not created by photons interacting with one another. It is created by the structure of those possibilities. So far the behaviour is strange, but still manageable. The rules are unfamiliar, but they are consistent. The real tension appears when the experiment is altered in a subtle way. A detector is placed near the slits, capable of determining which opening each photon passes through. Nothing else is changed. The light source remains the same. The screen remains the same. Only the possibility of knowing the path is introduced. The effect is immediate and unmistakable. The interference pattern disappears. In its place, two simple regions form on the screen, corresponding to the two slits. The photons now behave exactly as particles are expected to behave, each arriving in a way that reflects a single, definite path. Remove the detector and the interference returns. Restore it and the pattern vanishes again. The shift is sharp, not gradual. At first glance, this can sound as though reality itself is responding to being watched, as if the photon somehow knows when it is under observation and changes its behaviour accordingly. That interpretation is tempting, but it misses something important. What matters is not awareness. What matters is interaction. To determine which slit a photon passes through, the photon must interact with something physical. That interaction links the photon to the measuring device, and, through it, to the surrounding environment. In doing so, it alters the conditions that allow the different possibilities to overlap and interfere. When no path information exists, the photon's behaviour is described by a broad range of overlapping possibilities. When path information exists, even in principle, those possibilities are narrowed. The overlap is lost, and with it the interference pattern. The universe is not responding to curiosity, it is responding to contact. This distinction helps explain why the result feels so counterintuitive. Everyday experience trains the mind to expect objects to have definite positions and paths at all times. A thrown ball follows a trajectory. A dropped key falls straight down. There is no sense in which those objects explore multiple possibilities before settling on one. At very small scales, that intuition no longer applies. In the double-slit experiment, the interference pattern is not a picture of individual photons weaving intricate paths through space. It is a map of likelihoods, a record of where photons are more or less likely to arrive when the system is allowed to evolve freely. Each detection event taken on its own looks entirely ordinary, just a single dot on a screen. But taken together, those events reveal a deeper structure that only appears when constraints are removed. It is a bit like watching rain fall on a pavement. One drop tells you very little. Thousands of drops reveal the outline of the roof above. Measurement in this setting is not passive. It is not simply reading off a pre-existing fact. It is an active physical process that changes the system being measured. By asking a more specific question, the system is forced into a more specific state. Specificity comes at a cost. When left alone, light explores many possibilities at once. When constrained, it commits to one. This does not mean that reality is vague or incomplete until someone looks. It means that, at small scales, some properties do not exist in sharply defined form until interaction makes them so. The double-slit experiment does not suggest that the universe is irrational or chaotic. Its behaviour is precise, consistent, and repeatable. The same setup produces the same statistical pattern every time. The rules are clear, even if they are not the ones intuition expects. Interference is the clue that something wave-like is always present in the background, even when individual events appear particle-like at the moment of detection. Measurement reveals one outcome, but the pattern emerges from many. The lesson is not that light is confused about what it is that the categories of wave and particle are tools, not truths. Useful descriptions that work in some situations and quietly fail in others. When light moves freely, it behaves as if it is everywhere it could be. When it is forced to account for itself, it behaves as if it has always been somewhere specific. Both descriptions are accurate within their limits. Neither tells the whole story on its own. Left alone, reality is generous with possibilities. When pressed for an answer, it responds with a single, definite outcome. And in the space between those two behaviours lies the quiet strangeness that the double-slit experiment continues to reveal. As the strange results of experiments continued to accumulate, it became clear that physics needed a new way of speaking. Not just new ideas, but a new kind of language altogether. Light behaved like waves until it did not. Particles left individual marks while somehow building wave patterns. The familiar tools of classical motion Neat paths traced through space and time were no longer enough to describe what was being seen. What was missing was not intuition, but structure. That structure arrived in the form of a mathematical framework developed by Erwin Schrödinger, a physicist who hoped, perhaps optimistically, to restore some sense of continuity to the quantum world. His aim was not to make reality stranger, but to describe it more gently, using smooth change rather than abrupt jumps wherever possible. What emerged from this effort was an equation that would become central to quantum physics, not because it offered easy answers, but because it offered a consistent way to track how quantum systems evolve. It is often called Schrödinger's equation, but thinking of it as a formula to be solved misses its real role. It is better understood as a set of instructions. Given a quantum system as it is now, the equation tells how that system changes over time, not where a particle will be found and not what outcome will occur, but how the range of possibilities reshapes itself moment by moment. At the heart of this description lies the wave function. Despite its name, the wave function is not a physical wave rippling through space. It does not slosh or vibrate or carry substance from one place to another. It is a description, a compact mathematical summary of everything that can be said about a system's possible states. Where a particle might be found, how likely each possibility is, which energies are allowed, which outcomes are forbidden. The wave function does not tell a particle where it is, it tells the universe where the particle could be. This shift is subtle but profound. In classical physics, motion is described as a sequence of positions. At each moment, an object occupies a specific point in space and moves smoothly to the next. Given enough information, the entire path can be traced in advance. Uncertainty, when it appears, usually reflects missing knowledge rather than a limitation of nature itself. In the quantum world, that picture dissolves. Instead of a single path, a particle is described by a spread of possibilities, a probability cloud rather than a line. Some regions are more likely than others, but none are guaranteed until an interaction occurs. Between measurements, the particle does not travel from one definite place to another in the familiar sense. Its wave function evolves, reshaping the landscape of likelihoods as time passes. This does not mean the particle is vague or ill-defined. It means the description has changed. Precision now applies to probabilities rather than positions. Schrödinger's equation governs how these probability clouds move and change. It tells how they spread, how they shift, how they interfere with themselves, and how they respond to forces. Importantly, it does all of this smoothly. There are no sudden jumps in the evolution of the wave function itself. The mathematics is calm, continuous, and exact. The uncertainty appears only when a specific outcome is demanded. This distinction is often overlooked. Quantum physics is not unpredictable because its laws are sloppy. The laws are precise to an extraordinary degree. Given a wave function, its future evolution can be calculated exactly. What cannot be predicted is which single outcome will be realized when a measurement takes place. That randomness is not a flaw, it is a feature. To make sense of this, it helps to think again in terms of clouds rather than paths. Imagine releasing a faint mist into still air. At first, it is concentrated in one place. Over time, it spreads, thinning in some regions and thickening in others depending on subtle currents. The mist does not follow a line. It occupies a region with varying density. A probability cloud behaves in a similar way. Where the cloud is denser, the particle is more likely to be found. Where it is thinner, less likely. But until interaction occurs, the cloud itself is the most complete description available. When a measurement happens, the cloud does not slowly narrow. It resolves into a specific outcome. The particle is found in one place, with one value of energy or motion. The probabilities have done their job. One possibility has been realized. Before that moment, asking for a precise position is like asking for the exact location of a sound before it is played. The question does not yet apply. This reimagining of motion can feel unsettling because it challenges deeply ingrained habits of thought. Everyday experience insists that objects are always somewhere, moving along well-defined routes whether anyone looks or not. That intuition works beautifully at large scales, where probability clouds are so tightly packed that they behave like solid points. At small scales, the clouds are wider, and their spread can no longer be ignored. The wave function does not represent ignorance. It represents completeness. It is not hiding a secret path behind a curtain. It is telling the full story that nature allows at that scale. Trying to force a sharper picture onto it does not reveal more truth. It introduces confusion. This is why it matters to treat the wave function as a description, not an object. It is not something a particle carries around. It is not a physical mist filling space. It is a rule book for how possibilities behave. Different interpretations of quantum physics disagree about whether the wave function should be considered real in some deeper sense, but all agree on its practical role. It works. It predicts experimental results with astonishing accuracy. It explains why atoms are stable, why certain energies appear and others do not, and why particles can behave in ways that no classical object ever could. Most importantly, it replaces the idea of fixed paths with something more flexible. Motion, at the smallest scales, is no longer about tracking where something is at every instant. It is about tracking how likelihoods flow. A particle moves not because it follows a line, but because the center of its probability cloud shifts. Its behavior emerges from the changing shape of possibility itself. In many situations, these clouds remain tightly confined. Their motion closely mimics classical trajectories, which is why the everyday world feels so solid and predictable. In other situations, the clouds spread, overlap, and interfere, producing effects that have no classical counterpart. The mathematics allows for both, without contradiction. Schrodinger himself hoped that this wave-based picture would soften the harsher edges of quantum theory, restoring a sense of continuity that the idea of sudden collapses seemed to threaten. In some ways, it does. The evolution of the wave function is gentle, lawful, and smooth. The strangeness enters not through the mathematics, but through what is asked of it. When no specific outcome is required, the universe is content to carry many possibilities at once. When an outcome is demanded, one is selected and the rest fall away. The mathematics does not say why that particular outcome occurs, only how likely it was. This is not a failure of explanation. It is a statement about the structure of reality. At the smallest scales, the universe does not commit itself to a single story until interaction forces the issue. Until then, it moves through a space of possibilities, guided by precise rules that favour some outcomes over others. Solid paths give way to probability clouds. Deterministic motion gives way to evolving likelihoods. What replaces certainty is not chaos, but a quieter, more subtle order. The mathematics of possibility does not strip meaning from the world. It reshapes it. And in doing so, it offers a picture of motion that is less rigid, more flexible, and in its own way, deeply elegant. By the time quantum ideas had begun to settle into a workable framework, a new discomfort made itself known. Even with careful mathematics and beautifully predictive equations, there remained a sense that something fundamental was slipping through the fingers. Not a gap in knowledge that better tools might fix, but a limit that refused to move no matter how gently it was approached. This limit became known as the uncertainty principle, and it has been misunderstood almost from the moment it was introduced. At first hearing, It sounds like a confession of failure, a statement that measurements are clumsy, that instruments interfere too much, that precision is lost because the act of looking gets in the way. Shine light to see a particle, and the light knocks it about. Try to pin down its motion, and the act of pinning disturbs it. From this point of view, uncertainty feels like an engineering problem waiting for a better solution. But that explanation, comforting as it may be, misses the point. The uncertainty principle is not about limitations of technology, and it is not about careless measurement. Even in a perfectly quiet universe, with perfect instruments and infinite patience, the uncertainty would remain. It is not imposed from the outside. It is woven into the structure of nature itself. To understand why, it helps to think again in terms of waves and probability clouds rather than solid points. A particle described by a wave function does not occupy a single location. Its presence is spread out, more here, less there, with no sharp boundary. That spread is not a blur caused by ignorance. It is the most complete description available. Now imagine trying to squeeze that spread into something narrower. The more tightly the cloud is confined in space, the more complicated its internal structure must become. It begins to include a wider range of motions. Precision in position comes at the cost of precision in motion, not because something has gone wrong, but because waves behave that way. This trade-off is unavoidable. It is not a statement about what can be known. It is a statement about what can exist. Trying to specify both position and motion with perfect accuracy is like trying to describe a melody using a single instant of sound. The request itself asks for more than the phenomenon can provide. The universe does not store that information because it is not part of how things are organized. This is why the uncertainty principle feels so different from everyday experience. In daily life, objects appear to have definite positions and definite motions at all times. A car moves down a road, a thrown stone follows a clear arc. Nothing seems blurry or ambiguous. But those objects are made of vast numbers of particles. Their individual uncertainties overlap and average out, producing behaviour that appears crisp and deterministic. The blur is still there, but it is buried beneath scale. At small scales, there is nowhere for it to hide. A helpful way to picture this is fog. Standing in thick fog, it is possible to tell roughly where something is, but not precisely. Move closer, and its position becomes clearer. At the same time, its direction of motion becomes harder to judge. Step back, and the direction becomes clearer, but the position softens again. There is no single vantage point where everything snaps into perfect focus. The fog is not hiding something sharp. The fog is the situation. Or consider touch. Trying to locate a delicate object with bare hands often requires compromise. Press gently, and its exact position is uncertain. Press firmly, and its motion changes. There's no way to extract perfect information without altering the state of what is being touched. The uncertainty principle expresses this kind of balance, elevated from everyday experience to a fundamental rule. One of the most important consequences of this rule is that it rules out certain classical fantasies entirely. There is no hidden ledger beneath the surface where every particle carries an exact position and an exact motion at all times, waiting to be revealed. The uncertainty is not about missing information. It is about the absence of that information altogether. Nature refuses that level of precision. This refusal is not sloppy or approximate. The uncertainty principle is exact. The boundary it draws is sharp and unyielding. It does not say that nothing can be known. It says that some pairs of properties cannot be defined simultaneously beyond a certain limit, because defining one necessarily loosens the other. Within that limit, quantum physics remains astonishingly predictive. The probabilities it assigns are precise. The patterns it forecasts are reliable. What it does not offer is certainty about individual outcomes, and it never promises to. This built-in blur reshapes how motion itself is understood. In the quantum world, motion is not the steady sliding of a point along a path. It is the evolution of a distribution, a shifting pattern of likelihoods that flows and reshapes itself over time. A particle moves because its probability cloud moves. The centre of that cloud drifts. Its shape may stretch or compress. But it never collapses into a perfectly sharp point while retaining a perfectly sharp motion. This blur is not a flaw to be corrected. It is what allows the quantum world to function at all. Without it, atoms would not be stable. Electrons would collapse into nuclei. Matter would lose its structure. Chemistry would fail. Biology would never emerge. The uncertainty that feels so uncomfortable at first glance turns out to be the quiet guardian of complexity. There is a strange kindness in that. What appears as a restriction is actually a protection. The blur prevents the universe from becoming too rigid, too brittle. It allows systems to settle into stable arrangements rather than spiraling into extremes. This does not mean the world is fuzzy everywhere. At large scales, the uncertainty becomes vanishingly small. The fog thins. Paths reappear. Classical physics takes over, not because quantum rules stop applying, but because their consequences are drowned out by scale. At small scales, the fog remains thick. The uncertainty principle does not say that reality is unknowable. It says that reality is structured in a way that resists absolute sharpness. Some questions simply ask for more precision than nature is willing to provide. Once that is accepted, the principle stops feeling like a barrier and starts feeling like a guide. It tells where classical intuition can be trusted and where it must be softened. It marks the boundary between solid expectations and a more fluid way of thinking. The built-in blur is not an error to be fixed, it is a feature to be understood. It is the quiet softness at the heart of the quantum world, ensuring that nothing is ever pinned down too tightly, and that possibility always has room to move. One of the most persistent ideas in everyday thinking is that things must always be one way or another, here or there, moving or still, on or off. It feels natural to assume that reality makes up its mind immediately and then sticks with the decision. At large scales, that assumption works beautifully. At very small scales, it quietly falls apart. In quantum physics, systems do not rush to choose. They linger in a state of possibility, carrying several potential outcomes at once. This behaviour is known as superposition, and despite its reputation for sounding mystical or absurd, it is best understood as something calm, practical, and deeply ordinary once the right picture is in place. Superposition does not mean that a particle is confused, conflicted, or half-finished. It means that, before interaction demands a specific answer, the system is described by more than one allowed state at the same time. These states coexist, each weighted by how likely it is to appear when the moment comes. This coexistence is not a failure to decide, it is the natural default. To see why, it helps to return to the idea of the wave function. The wave function does not point to a single outcome. It describes a spread of possibilities, each one mathematically present and evolving smoothly over time. As long as the system is left alone, nothing inside the mathematics forces one possibility to be selected over the others. There is no hidden clock counting down to a decision. The system does not choose because nothing requires it to. In classical physics, change is driven by forces acting on objects with definite properties. Push something, and it moves. Pull it back, and it slows. The present determines the future in a continuous chain. In the quantum picture, the rules are different. The wave function evolves according to precise laws, but those laws govern probabilities, not outcomes. As time passes, the distribution of possibilities shifts, stretches, and reshapes itself. Some outcomes become more likely, others fade. But until interaction occurs, all allowed outcomes remain part of the description. This is what superposition really means. It is the coexistence of futures. A quantum system can be in a superposition of positions, meaning there are several places it could be found. It can be in a superposition of energies, meaning it does not possess a single definite energy until interaction demands one. These are not vague states. They are sharply defined sets of possibilities, each with its own mathematical weight. The outcomes themselves are never blurry. When a result appears, it is always definite. The blur exists only in the range of options before that moment. This distinction matters because it dissolves many common misunderstandings. A particle in superposition is not smeared halfway across space in a physical sense. It is not partly here and partly there, like paint dragged across a canvas. It is fully capable of being found in several different places, and until interaction occurs, none of those possibilities has been excluded. Measurement is where the narrowing happens. When a quantum system interacts with something large enough to register an outcome, the range of possibilities contracts. One option becomes real, the others fall away. This is often described as collapse, but that word can suggest something violent or dramatic, as if reality were shattering into place. In practice, the process is quieter. Measurement does not create an outcome from nothing. It selects one from the set that already existed. The system does not invent a new property at the moment of interaction. It reveals one that was already allowed. A helpful way to think about this is to imagine a wide beam of light passing through an adjustable opening. Before the opening, the light spreads broadly. After it, the beam is constrained. The light itself has not changed its nature. The range of paths it can take has simply been limited. Measurement works in much the same way. It narrows what is possible. This perspective removes the temptation to think of observation as magical or consciousness-driven. Nothing waits for awareness. Nothing snaps into place because it is noticed. What matters is physical interaction. When a system becomes linked to its surroundings in a way that records an outcome, the superposition can no longer be maintained. The universe does not demand an answer until it has to. This reluctance to choose is not a flaw. It is an advantage. By allowing multiple possibilities to coexist, quantum systems can behave in ways that would otherwise be impossible. Interference patterns arise because overlapping possibilities can reinforce or cancel one another. Tunneling occurs because the range of allowed states includes outcomes beyond barriers that classical objects cannot cross. Atomic stability emerges because electrons exist in superpositions that spread them out rather than forcing them into precise orbits. Without superposition, the quantum world would be brittle. Systems would collapse into extremes. Structure would be lost. Even technologies that now feel cutting edge rely on this quiet feature. Quantum computing, for example, takes advantage of systems that can carry multiple potential answers forward at the same time. The power does not come from speed alone, but from breadth, from allowing many possibilities to evolve together before narrowing them down. Nature has been doing this long before humans noticed. Photosynthesis appears to exploit superposition to move energy efficiently through complex molecular structures. Certain biological processes seem to maintain quantum coherence just long enough to gain an advantage. These effects are subtle and delicate, but they point to the same underlying principle. Keeping options open can be useful. At larger scales, this behaviour becomes difficult to see because interaction happens constantly. Air molecules collide, light scatters, heat flows. Superpositions are narrowed almost immediately, leaving only one outcome visible. This is why everyday objects appear definite and stable. They are never isolated long enough to remain otherwise. At small scales, where isolation is possible, the openness remains. Superposition is often described as strange because it conflicts with habits formed in a classical world. But strangeness is not the same as incoherence. The rules governing superposition are precise, testable, and reliable. Experiments confirm them again and again. The discomfort comes from expectation, not from behaviour. The universe does not insist on being one thing at a time. It allows itself to be many things until interaction demands a choice. This generosity of possibility is not chaos. It is structured, weighted, and guided by exact laws. Once that is understood, superposition stops feeling like a paradox and starts feeling like a design choice. Reality does not hurry. It does not rush towards certainty. It carries its options forward calmly, letting them evolve, overlap, and influence one another until a boundary is imposed. Only then does it choose, and when it does, the choice is clean, definite, and final, not because the other possibilities were never there, but because their time has passed. Being many things at once is not a mistake. It is how the quantum world makes room for complexity, stability, and change all at the same time. Distance feels authoritative in everyday life. Two objects close together can influence one another easily. Two objects far apart cannot. Space separates, delays, and protects causality. This expectation is so deeply ingrained that it rarely feels like an assumption at all. It feels like a fact. At the quantum level, that confidence begins to soften. When two quantum systems interact in certain ways, they can become linked so thoroughly that describing one without the other no longer makes sense. Their properties stop belonging to them individually and begin to belong to the pair as a whole. This linking is called entanglement, and it is not about mysterious forces reaching across space. It is about relationships that refuse to break when distance is introduced. To understand entanglement, it helps to stop thinking in terms of individual objects and start thinking in terms of shared descriptions. In classical physics, systems carry their own properties wherever they go. After two objects interact and separate, each continues on with its own independent state. Any connection that existed between them ends at separation. Quantum systems do not always behave this way. When two particles interact and become entangled, the wave function that describes them no longer splits neatly into two separate parts. Instead, there is a single description that applies to both together. Certain properties remain undefined individually, but the relationship between them becomes sharply defined. This is the heart of entanglement. The particles do not each carry complete instructions. The instructions are shared. Imagine preparing two particles in such a way that when one is found to have a particular property, the other must have a corresponding one. The specific outcomes are not fixed in advance, but the correlation is, whatever happens here must be consistent with whatever happens there. Once the particles move apart, that correlation remains intact. This is where discomfort begins to creep in. If one particle is measured and a result is obtained, the outcome for the distant particle is immediately constrained. The shared description updates. It can feel as though information has travelled instantly from one location to another, as though space itself has been bypassed. This impression troubled Albert Einstein deeply. Einstein was not opposed to quantum mechanics as a predictive framework. He helped build it. But he was uneasy with any picture of reality that seemed to allow influences without mediation through space. For him, locality mattered. Causes should not leap across distance. Nothing should outrun light. Entanglement appeared to challenge that principle. Einstein famously referred to it as a kind of spooky action at a distance, not as a compliment, but as a warning. Something about the theory, he felt, was incomplete, and yet careful examination shows that entanglement does not violate relativity. The key is understanding correlation without communication. When a measurement is made on one member of an entangled pair, the outcome is random. It cannot be chosen or controlled. The same is true for the distant particle. Its outcome is not caused by the measurement elsewhere. It is constrained by the shared structure of the entangled state. No message is sent. No signal travels. No information is transmitted in a way that could be used to communicate faster than light. The apparent instant update occurs in the description of the pair, not in physical space. Until the results from both locations are compared, which requires ordinary communication limited by the speed of light, nothing observable distinguishes entanglement from chance. The correlations only reveal themselves when data from both sides are brought together. Relativity remains intact. This distinction is subtle but essential. Entanglement does not allow control at distance, it allows consistency at a distance. The universe ensures that outcomes fit together properly, even when they are separated by vast stretches of space. It does this not by sending messages, but by never assigning independent properties in the first place. The correlation was built in from the start. A common way of explaining this uses the idea of paired objects prepared together and then separated. If one is found to have a certain feature, the other must have the complementary one. The everyday version of this story often involves gloves placed in boxes and sent far apart. Open one box and the contents of the other are immediately known. But that analogy only goes so far. In the glove example, the properties were fixed in advance. One glove was always left-handed, the other right-handed. The information existed all along. In quantum entanglement, the outcomes are not predetermined in that way. The universe commits to the relationship without committing to the individual values until measurement occurs. Consistency is guaranteed, but specifics are left open. This is what unsettled Einstein. He suspected that hidden details must exist beneath the surface, quietly assigning definite properties ahead of time. Over the years, experiments were designed to test this possibility. Again and again, the results favoured the quantum description. Nature appeared to resist being reduced to hidden classical instructions. Entanglement is not rare or exotic. It arises naturally whenever quantum systems interact and then separate without completely losing coherence. It plays a role in the structure of atoms, in chemical bonding, and in the collective behaviour of particles and solids. It is not an anomaly. It is part of the fabric of the quantum world. It has also become a practical resource. Technologies such as quantum cryptography rely on entanglement to ensure security. Any attempt to intercept or copy an entangled system disturbs it in detectable ways. The same relational structure that once seemed philosophically troubling becomes, in this context, extremely useful. What makes entanglement powerful is not mystery but limitation. The impossibility of copying entangled states and the impossibility of controlling outcomes at a distance are not bugs. They are features that protect the integrity of the correlations. Seen this way, entanglement does not undermine causality. It reframes it. Cause and effect still respect the speed of a light. What changes is the idea that systems must always carry their own independent properties. At small scales, reality appears to be organized around relationships first, with individual attributes emerging only when interaction demands them. Distance in this picture is not the ultimate divider. Two particles that were once connected can remain part of a single description even when space grows between them. Their separation does not erase the history of their interaction. The universe remembers how they were linked. Entanglement does not suggest that everything is secretly connected to everything else. It suggests that when connections exist, they matter deeply, and they do not dissolve simply because objects move apart. The discomfort surrounding entanglement often comes from trying to force it into classical categories. Is something travelling between the particles or not? Is information moving or not? These questions assume that the only way to maintain consistency is through transmission. Quantum physics offers another option. Consistency can be global rather than local. Relationships can be fundamental rather than derivative. Einstein's unease was an honest response to a genuine shift in perspective. He recognized that something profound was being claimed, and he demanded clarity. Over time, that clarity has grown, even if the picture remains unfamiliar. Entanglement does not abolish space. It does not allow signals to outrun light. It does not turn the universe into a chaotic web of instant influence. It reveals something quieter. Across any distance, the quantum world can maintain relationships that are stronger than separation, ensuring that when outcomes finally appear, they do so in perfect agreement with a structure that was shared all along. There are few images in science as famous or as persistently misunderstood as a cat sealed inside a box. It appears again and again in explanations of quantum physics, often presented as proof that the universe is absurd, paradoxical, or deliberately mischievous. A cat, the story goes, is somehow both alive and dead at the same time, suspended in a strange limbo until someone opens the lid and looks inside. It is memorable, unsettling, and almost always presented as a literal claim about how reality behaves. That is precisely why it causes so much confusion. The scenario involving the cat was never meant as a statement about the world. It was a critique, a carefully designed objection meant to expose a problem in how quantum ideas were being interpreted. Schrodinger did not introduce the cat to celebrate quantum strangeness, but to question how far certain explanations could reasonably be pushed before they stopped making sense. To understand what the thought experiment was actually targeting, it helps to return to the unease that motivated it. By the early 1930s, quantum mechanics had already proven its power. It described atoms with remarkable accuracy, predicted spectral lines, and explained how light and matter interact at small scales. Experiment after experiment confirmed its predictions. And yet, despite this success, something about its interpretation felt unfinished. The mathematics described smooth, continuous evolution. Measurements produced single, definite outcomes. Somewhere between those two facts sat a gap that had not been fully explained. Quantum systems could exist in superpositions, carrying multiple possible outcomes at once, but measurements never revealed that multiplicity. They revealed only one result. What exactly was happening in between? Schrodinger was troubled by how casually this question was sometimes set aside. To make the issue impossible to ignore, he proposed an exaggerated scenario that deliberately stretched quantum reasoning into an uncomfortable domain. A sealed box contained a cat, a radioactive atom, and a device triggered by the atom's decay. If the atom decays, the device activates. If it does not, nothing happens. The atom itself can be described as existing in a superposition of decayed and not decayed. If that description is taken at face value and applied without qualification, Schrodinger asked, what does it imply about the cat inside the box? The discomfort produced by this question is not an accident. It is the entire point. Schrodinger was not suggesting that cats genuinely exist in such states. He was showing that something had gone wrong in the way the theory was being interpreted. The cat is not the claim, it is the warning. Much of the misunderstanding comes from blurring the line between measurement and knowledge. It is tempting to imagine measurement as an act of awareness, as if learning the outcome somehow causes it to happen. Open the box, see the cat, and reality snaps into place. This framing feels intuitive because it mirrors human experience, but it does not reflect how quantum physics actually works. Knowledge is not a physical process. Interaction is. Long before anyone opens the box, the system inside is already interacting relentlessly. The radioactive atom interacts with its surroundings. The triggering device interacts with the air, the walls, and itself. The cat interacts continuously with its environment, producing heat, motion, sound, and countless microscopic disturbances. These interactions matter because they entangle the system with its surroundings. As this entanglement spreads, the delicate superpositions that can exist in carefully isolated quantum systems become distributed across many degrees of freedom. The different possible outcomes become tied to different states of the environment. Once that happens, maintaining a coherent superposition is no longer possible in practice. The outcome becomes definite not because someone knows it, but because the system has become irreversibly linked to the world around it. By the time the box is opened, the result has already been settled by physical processes. Opening the box reveals what happened. It does not cause it to happen. This is where macroscopic intuition fails when applied too directly to quantum ideas. Superposition is not a universal condition. It is fragile. It requires isolation. The larger and more complex a system becomes, the harder it is to shield from interaction with its environment. Large objects are never left alone. They are constantly measured by their surroundings through heat exchange, collisions, and radiation. A cat is not a single quantum system. It is an enormous, noisy collection of interacting parts. There is no sharp boundary where the quantum world suddenly switches off and the classical world begins. Instead, there is a gradual transition. As systems grow larger and more entangled with their environments, superpositions become less accessible, and classical behaviour emerges naturally. The quantum rules still apply, but their effects are drowned out by scale. The cat thought experiment exposes the danger of ignoring this transition. It shows what happens when quantum descriptions are extended without care into regimes where their usual assumptions no longer hold. The mathematics remains correct, but the interpretation becomes misleading. The wave function does not say that a cat is physically alive and dead at the same time. It describes a range of possible outcomes under specific conditions. When those conditions include strong, unavoidable interaction with an environment, only one outcome survives. Schrödinger's objection was not to quantum mechanics itself, but to the idea that its mathematical descriptions could be treated as literal pictures of macroscopic reality without adjustment. The theory works extraordinarily well, but its meaning depends on context. The thought experiment also reveals a deeper lesson about storytelling in physics. Quantum mechanics is not a narrative theory. It does not describe what is happening moment by moment in the way classical stories do. It describes probabilities, relationships, and constraints. When those descriptions are forced into familiar story shapes, paradoxes often appear. The cat in the box is one such paradox, created not by nature but by misplaced expectations. This does not dissolve every mystery. Questions about measurement and interpretation remain open and actively explored. Different approaches offer different ways of understanding how definite outcomes arise. But none require consciousness to play a special role, and none suggest that reality waits to be noticed before it decides what to do. What reality responds to is interaction. Macroscopic intuition struggles because it is built in a world where interaction is constant and overwhelming. Objects have definite properties because they cannot avoid being measured by their surroundings. At microscopic scales where isolation is possible, the rules look different. The cat thought experiment forces these two domains into contact, revealing where intuition must be softened and where it must be let go entirely. It reminds us that metaphors are tools, not truths, and that even the most vivid image can mislead if taken too literally. Schrödinger chose a cat precisely because it felt absurd. He wanted the discomfort to be unmistakable. In doing so, he created one of the most enduring images in science, even if it has often been used in ways he never intended. When understood carefully, the experiment does not suggest that reality is nonsensical. It suggests that translation between mathematics and mental pictures requires care. Quantum mechanics is subtle, not silly. and its strangeness often reflects the limits of intuition rather than the behaviour of the world itself. Once that distinction is clear, the paradox softens, the cat steps out of the spotlight, and the real lesson remains quietly in place. In the everyday world, barriers are decisive. A wall blocks a path. A locked door stops movement. If something lacks the energy to climb over an obstacle, it stays where it is. This intuition is so reliable that it rarely feels like an assumption. It feels like a rule. At the quantum scale, that rule becomes more flexible. Quantum tunneling is the name given to a behaviour that seems to defy common sense at first glance. Particles appear on the far side of barriers they do not have enough energy to cross. They slip through regions that classical physics would label strictly forbidden, not by smashing through, and not by going around, but by quietly appearing where they should not be able to reach. This is not a trick, and it is not rare. It is a direct consequence of how quantum systems are described. To understand tunneling, it helps to return once more to probability clouds rather than solid objects. In classical physics, a particle is imagined as a point with a definite energy. If it approaches a barrier that requires more energy than it possesses, the story ends. The particle turns back. There is nowhere else for it to go. In quantum physics, the description is different. A particle is represented by a wave function, a spread of possibilities rather than a single location. That spread does not stop abruptly at sharp boundaries. It tapers, it fades, it leaks. When a quantum particle approaches a barrier, its probability cloud does not pile up neatly on one side and vanish on the other. Instead, the cloud extends slightly into the barrier itself. The likelihood of finding the particle there drops rapidly, but it does not fall to zero immediately. And sometimes that faint tail reaches all the way through. This is the essence of tunneling. The particle does not climb over the barrier. It does not punch a hole through it. The probability of finding the particle on the far side is small, but it is not zero. And when probability is allowed, events eventually occur. Forbidden, in quantum physics, does not mean impossible. It means unlikely. This distinction is subtle but powerful. Classical rules draw hard lines. Quantum rules draw gradients. Instead of absolute boundaries, there are regions of diminishing likelihood. Most of the time, the particle behaves exactly as classical intuition expects. Occasionally, it does something that feels impossible only because the probability was low. Low probability events are not violations of rules. They are part of the rules. A helpful way to picture this is to imagine a hill in thick fog. In clear air, it is obvious whether something has enough energy to climb to the top. In fog, that certainty softens. There is a region near the top where presence becomes unlikely but not sharply forbidden. A wanderer might appear briefly where they should not be able to reach, simply because the boundary is no longer precise. Quantum barriers behave more like foggy hills than solid walls. This leaking of probability is not a philosophical curiosity. It plays a central role in some of the most important processes in nature. Radioactive decay, for example, relies on tunneling. Certain atomic nuclei are stable only because the particles inside them are confined by energy barriers. Classically, those particles do not have enough energy to escape, and yet, over time, some do. They tunnel out, leading to decay. The timing of these events cannot be predicted for any single nucleus, but the probability can be calculated with extraordinary accuracy. This is why radioactive half-lives are so reliable. The barrier is real, the escape is rare, but rare is not never. Tunneling also plays a crucial role at the heart of stars. In the cores of stars like the Sun, atomic nuclei are packed together under immense pressure and heat. For fusion to occur, positively charged nuclei must come close enough for the strong nuclear force to bind them together. Classically, their electrical repulsion should keep them apart. The energy required to overcome that repulsion is far higher than the thermal energy available in the core. And yet, fusion happens. It happens because quantum tunneling allows nuclei to slip through the barrier of electrical repulsion. Most attempts fail. The probability is small, but there are vast numbers of nuclei and enormous amounts of time. Even rare events become common when conditions persist long enough. Without tunneling, stars would not shine. The sun would never ignite. The universe would be a darker, colder place. Closer to home, tunneling also underlies technologies that make the modern world possible. Devices that rely on precise control of electrons, such as certain types of microscopes and electronic components, take advantage of the fact that electrons can tunnel through barriers that classical physics would deem impenetrable. Once again, what feels strange turns out to be useful. The key to all of this is letting go of the idea that particles must always behave like tiny balls obeying rigid rules. Quantum particles are not points following paths. They are patterns of possibility evolving over time. Barriers do not shut those patterns off abruptly. They reshape them. Most of the probability reflects back. A small portion seeps through. That seepage is tunneling. It is important to note what tunneling does not imply. It does not allow particles to teleport freely. It does not let energy appear from nowhere. The probabilities involved decrease rapidly as barriers grow thicker or taller. For large objects and everyday obstacles, the chance of tunneling is so vanishingly small that it might as well be zero. This is why people do not fall through floors, and walls do not quietly let objects pass. The rules scale with size. What is possible for electrons is effectively impossible for cats. Quantum tunneling does not break causality or conservation. It respects the same underlying laws. It simply applies them through probabilities rather than certainties. In a quantum world, asking whether something can happen is often the wrong question. The more meaningful question is how likely it is. When a barrier is described as forbidden, it means that the probability of passage is extremely low, not that it is absolutely excluded. The language of impossibility belongs to classical thinking. Quantum physics replaces it with a softer vocabulary, unlikely, rare, suppressed, but never quite impossible. This gentle loosening of boundaries is one of the reasons the quantum world feels so different from everyday experience. It trades rigid rules for smooth transitions. It allows nature to explore edges rather than stop abruptly at them. And in doing so, it makes room for processes that would otherwise never occur. Stars shine, atoms decay, electrons flow, all because probability is allowed to leak where classical certainty would draw a firm line. Quantum tunneling is not about breaking rules. It is about discovering that the rules were never as absolute as they first appeared. Empty space feels simple. Step outside on a quiet night, look up at the dark between the stars, and it appears almost self-explanatory. Nothing there. No matter, no motion, just absence. For most of human history, this intuition went largely unchallenged. Space was treated as a passive backdrop, a silent stage on which physical events unfolded, but never something that took part in those events itself. Quantum physics offers a different picture, not loudly or dramatically, but with quiet insistence. At very small scales, the idea of a perfectly empty vacuum begins to lose its meaning. What looks like nothingness turns out to have structure, energy, and activity woven into it, not in the form of obvious motion, but as a kind of perpetual restlessness that never quite disappears. The shift begins with a deceptively simple question. What is the lowest possible energy a system can have? In classical thinking, the answer is zero. Remove all energy, eliminate all motion, and what remains is complete stillness. A pendulum at rest, a particle sitting quietly in place, a universe drained of activity. There is nothing left to give. Quantum systems do not allow this outcome. Because of the uncertainty built into nature, certain properties cannot both be pinned down perfectly at the same time. If a system were brought to complete rest, its position would need to be known with absolute precision, and that combination is not permitted by the rules governing quantum behaviour. As a result, even in the calmest state available, a small amount of motion remains. This residual motion is known as zero-point energy. It is not excess energy that can be extracted or harvested. It is not hidden fuel waiting to be tapped. It is simply the minimum background activity required by the structure of quantum physics itself, a gentle, unavoidable jitter that persists even when every effort has been made to remove motion and heat. When this idea is extended beyond individual particles to space itself, the implications become striking. In quantum theory, space is not an empty container. It is filled with fields, and those fields cannot be perfectly still. Even in their lowest energy states, they fluctuate slightly. They rise and fall, stretch and relax in patterns that never fully settle into silence. This background state is called the quantum vacuum, though the word vacuum can be misleading. It suggests emptiness, when what is really being described is the calmest possible configuration of all the fields that exist, not nothing, but the quietest something nature allows. Within this calm, fluctuations occur continuously. These fluctuations are often described using the language of virtual particles, a phrase that has taken on a life of its own in popular explanations. It is tempting to imagine tiny particles popping in and out of existence like sparks, briefly appearing before vanishing again. That picture is vivid, but it should not be taken too literally. Virtual particles are not objects in the everyday sense. They are not little beads darting through space. They are better understood as temporary disturbances in fields, features of the mathematics that influence how interactions unfold, without ever becoming directly observable on their own. They're accounting tools that reflect the restless nature of the vacuum, rather than physical things waiting to be seen. Even so, their effects are real. One of the clearest demonstrations comes from what is known as the Casimir effect. Place two uncharged metal plates very close together in a vacuum. According to classical expectations, nothing remarkable should happen. There's no electric attraction and no magnetic pull, just two pieces of metal facing one another in empty space, yet a small force appears, drawing the plates together. This happens because the quantum vacuum between the plates is not the same as the vacuum outside them. Certain fluctuations are suppressed in the narrow gap, while others remain possible outside. The imbalance produces a pressure difference, gently pushing the plates inward. Nothing is added. Nothing is switched on. The vacuum itself is responsible. This effect has been measured repeatedly and agrees precisely with theoretical predictions. It is not a curiosity or a loophole. It is a direct consequence of the fact that empty space, in quantum physics, has behaviour of its own. The vacuum also influences the properties of particles. An electron, for example, is never truly isolated. It interacts constantly with surrounding fields, including those that make up the vacuum itself. These interactions slightly adjust its measurable properties, such as its energy and magnetic behaviour. The corrections are small, but they are precise, and experiments confirm them to extraordinary accuracy. Background activity matters. It is important to clear away a common misconception here. The quantum vacuum is not a reservoir of free energy waiting to be exploited. Its fluctuations cannot be tapped without cost, and they obey strict conservation rules. There is no hidden power source buried in empty space. What the vacuum provides is not fuel, but structure. It sets the baseline against which all other energies are measured. It shapes how forces behave and how particles interact. Without it, the predictions of quantum theory would not match the world that is observed. This reframing of emptiness explains why the vacuum feels so unintuitive. In everyday experience, emptiness means absence. Remove the air from a container, and what remains feels like nothing at all. At quantum scales, removing particles is not enough. The fields remain, and with them, their unavoidable fluctuations. Even at absolute zero temperature, when all thermal motion has been stripped away, this background activity persists. Not violently, not chaotically, but reliably. The universe refuses to sit perfectly still. There is something quietly humbling in that. Even when asked to do nothing, the universe does the smallest amount of something instead. The restlessness is not noise, it is structure. This constant activity has far-reaching consequences. It influences the behaviour of particles, contributes to the stability of matter, and plays a role in the evolution of the universe itself. It also challenges the sharp boundary between something and nothing, suggesting that those categories may be less absolute than intuition assumes. Empty space, in the quantum picture, is not a blank canvas. It is an active baseline, a reference state with rules and behaviour of its own. Fluctuations are not intrusions into nothingness. They are what nothingness looks like when governed by quantum law. The restless void does not announce itself. It hums quietly beneath everything, shaping interactions and setting limits without demanding attention. And in that quiet persistence, it reveals another preference of the universe, not for stillness, but for gentle motion, even where nothing appears to be at all. Observation feels straightforward in everyday life. You look at something and it reveals itself. A cup sits on a table. A clock shows the time. The act of seeing seems passive, almost irrelevant to what is being seen. The world appears to exist fully formed, simply waiting to be noticed. Quantum physics unsettles that comfort, not by denying reality, but by asking what it really means to observe something at all. Early descriptions of quantum mechanics often spoke of wave functions collapsing when a measurement takes place. The phrase is memorable, and it has endured, but it can quietly mislead. Collapse sounds like a physical event, a sudden snap where anything vague becomes sharp, as if the universe were holding its breath until observation forced a decision. In practice, collapse is not a physical mechanism with a clear location or process. It is an idea, a way of accounting for the fact that quantum descriptions change once an outcome is registered. The mathematics before and after measurement is different, but the theory itself does not specify a dramatic moment where reality jumps from uncertainty to certainty. What it offers instead is a careful description of interaction. A quantum system left alone is described by a wave function that spreads across many possibilities. That description evolves smoothly and predictably over time. When the system interacts with something large enough to record an outcome, the description changes. Probabilities give way to a single result. The wave function no longer needs to track possibilities that can no longer occur. Calling this change a collapse is a convenient shorthand, but it risks implying more than the theory itself claims. What actually matters is not observation in the everyday sense, but measurement as a physical process. To measure something is to let it interact with another system in a way that leaves a trace. That trace might be a mark on a screen, a current in a circuit, or a change in a detector. In every case, the system being measured becomes linked to its environment. That linking is irreversible. Once information about a quantum system spreads into the surrounding world, the delicate balance of possibilities that existed before cannot be maintained. The system is no longer isolated. Its future behaviour must now be consistent with the record that has been created. This shift does not require awareness. It does not wait for understanding, attention, or thought. A detector left unattended will still record an outcome. A photographic plate will still darken. A cloud chamber will still trace paths. The universe does not check whether anyone is watching before it responds. This point is important, because consciousness has often been mistakenly elevated to a central role in quantum mechanics. The idea that reality depends on being observed by a mind is tempting, dramatic, and deeply misleading. It arises from confusing knowledge with interaction. Knowing something does not change it. Interacting with it does. When a quantum system interacts with a measuring device, both systems become entangled. The state of the system becomes correlated with the state of the device. As the correlation spreads to the environment through heat, vibration, light, and countless other channels, the range of possible outcomes narrows rapidly. What remains is one consistent story. From the perspective of the mathematics, this process looks like a reduction in possibilities. From the perspective of the physical world, it looks like an ordinary interaction playing out according to quantum rules. There is no special moment when reality waits for approval. The universe proceeds regardless. This understanding reframes the role of the observer. An observer is not a privileged participant. An observer is simply part of the environment, a complex system that becomes entangled with what it measures, just like any other physical object. This does not mean that all questions about measurement are settled. They are not. The transition from probability to outcome remains one of the most discussed aspects of quantum theory. Different interpretations offer different ways of thinking about what the mathematics represents and how outcomes emerge. Some interpretations treat collapse as a real physical process. Others deny that it exists at all, arguing that all possibilities continue to exist in different forms. Still others focus on the role of the environment in suppressing interference between outcomes, making only one result accessible. What they share is a commitment to explaining observations without invoking consciousness as a causal force. The calm way to approach these questions is to accept that quantum mechanics does not yet provide a single agreed-upon story about what is happening behind the scenes. What it provides instead is a set of rules that reliably connect preparation, interaction, and outcome. Those rules work extraordinarily well. The discomfort arises when there is a desire for more than the theory promises. Classical intuition wants a clear narrative, a sequence of definite events unfolding in space and time. Quantum mechanics offers something different. It offers correlations, probabilities, and constraints without insisting on a single underlying picture. This does not make the theory incomplete in a practical sense. It makes it modest. It describes what can be predicted and what cannot. It tells which questions have precise answers and which ones do not apply until interaction occurs. When a question demands more precision than the structure of reality allows, the theory refuses politely. Observation in this light is not a magical act. It is not a spotlight that creates reality where none existed. It is a process by which systems become connected, information spreads, and possibilities are reduced to outcomes. The wave function does not collapse because it is observed. It changes because the conditions have changed. This perspective also explains why the everyday world feels stable and definite. Large systems interact constantly with their surroundings. They are measured all the time by air molecules, photons, thermal vibrations, and countless other interactions. Their quantum possibilities are narrowed almost instantly, leaving no room for noticeable superpositions. At small scales, where isolation is possible, the openness remains longer. The question of what observation really means is still open in a deeper philosophical sense. Quantum mechanics leaves room for multiple interpretations, each attempting to clarify the relationship between mathematics and reality. These debates continue not because the theory fails, but because it succeeds so well that its implications cannot be ignored. The important thing is that none of these interpretations require awareness to play a special role. Reality does not wait for witnesses. It evolves according to rules that apply whether anyone is paying attention or not. Observation, stripped of its mystery, becomes something quieter and more grounded. It is interaction that leaves a trace, a physical process that links systems together and constrains what can happen next. Seen this way, the act of observing loses its drama but gains clarity. The universe is not performing for an audience, it is simply responding to contact, and in that response probabilities give way to outcomes, not because they are seen, but because they can no longer remain otherwise. Once quantum mechanics proved itself reliable, a new problem quietly took its place. The equations worked. The predictions matched experiments with astonishing precision. Atoms behaved as expected. Light and matter interacted exactly as the theory said they should. And yet, when it came to explaining what all of this meant, confidence thinned. Physicists found themselves in an unusual position. They had a framework that delivered correct answers again and again, but no single story that everyone agreed described what was really happening beneath the surface. Instead of one clear picture, there were several competing ways of interpreting the same mathematics. The most influential of these came to be known as the Copenhagen interpretation. Despite its name, it is not a single, rigid doctrine. It is better thought of as a family of ideas shaped by early pioneers of quantum theory, particularly Niels Bohr. At its core is a simple attitude. Quantum mechanics does not describe an objective reality independent of observation. It describes the outcomes of experiments. Asking what happens between measurements, in any deeper sense, is not always meaningful. This perspective is often misunderstood as evasive, but it was born out of pragmatism rather than philosophical laziness. The equations of quantum mechanics do not assign definite properties to systems before measurement. They assign probabilities. Those probabilities are not guesses. They are the most complete description the theory provides. From the Copenhagen point of view, demanding more than that is asking the theory to answer questions it was never designed to address. In this interpretation, the wave function is a tool for calculating the likelihood of different outcomes. It is not necessarily a physical object, nor a literal wave spreading through space. It represents knowledge about a system, not a hidden physical state waiting to be revealed. When a measurement occurs, the description changes because the situation has changed. New information is available. The old probabilities are no longer relevant. This approach has an undeniable appeal. It aligns closely with how the theory is actually used. Prepare a system, calculate probabilities, perform an experiment, compare results, repeat. The machinery works, and it works extraordinarily well. And yet for many, something feels unresolved. The Copenhagen interpretation is famously comfortable with ambiguity. It draws a line between what can be calculated and what can be meaningfully said, and it refuses to cross that line. Questions about what a particle is really doing when it is not being measured are met not with elaborate explanations, but with a gentle refusal. The theory does not answer that question. This restraint has frustrated generations of physicists and philosophers alike. It can feel unsatisfying to accept a theory that declines to provide a full picture of reality. Classical physics trained the mind to expect more. Given enough information, everything should be explainable. Every effect should have a clear cause. Every object should have definite properties at all times. Quantum mechanics resist that expectation. From the Copenhagen perspective, this resistance is not a flaw. It is a lesson. Nature at small scales does not conform to classical categories. Trying to force it into familiar stories leads to confusion rather than clarity. The role of physics, in this view, is not to satisfy metaphysical curiosity, but to describe what can be observed and predicted. This attitude is sometimes summarized by a phrase that has become both famous and infamous: shut up and calculate. Taken at face value, it sounds dismissive, even anti-intellectual. In practice, it reflects a hard-earned humility. The equations deliver answers, the experiments confirm them. Endless debate about what lies behind the mathematics does not improve predictions or build better devices. So calculations take priority. This does not mean physicists lack curiosity about deeper meaning. It means that, when forced to choose between philosophical completeness and practical success, most choose success. The history of quantum mechanics is filled with debates that produced no new predictions, while the calculations quietly continued to guide real discoveries. Ambiguity, in this sense, became tolerable. The Copenhagen interpretation does not claim to be the final word on reality. It claims to be sufficient. It accepts that the theory may be silent on some questions, and it treats that silence as a feature rather than a defect. If a question cannot be answered experimentally, the interpretation suggests that it may not be a physically meaningful question. This stance can feel unsettling, especially to those who expect physics to offer a complete account of what exists. But it also reflects a disciplined refusal to speculate beyond what evidence can support. There is a quiet discipline in that refusal. At the same time, the unease never entirely disappears. Many physicists accept the Copenhagen interpretation because it works, not because it satisfies them. They use it as a practical framework while remaining open to alternative interpretations that might offer a clearer picture without sacrificing accuracy. This tension has persisted for decades. On one side is the undeniable success of the theory. On the other is the lingering sense that something important remains unsaid. Rather than paralyzing progress, this tension has shaped it. Physicists learn to tolerate ambiguity, not as a failure of understanding, but as a boundary of the current framework. The calculations could proceed without a final answer to every philosophical question. Experiments could be designed, technologies could be built, insight could deepen, even if ultimate certainty remained out of reach. In a way, the Copenhagen interpretation reflects a broader lesson about science itself. The goal is not to produce comforting stories, it is to produce reliable predictions. When those predictions succeed, they earn trust, even if the interpretation that accompanies them feels incomplete. This does not close the door on deeper explanations, it simply refuses to force them prematurely. The phrase "shut up and calculate" is often quoted with a hint of rebellion, but it can also be read as an invitation to patience. Use the tools that work. Acknowledge what they do not yet explain. Leave room for future understanding. Choosing an interpretation, then, is not about allegiance. It is about emphasis. The Copenhagen approach emphasizes restraint, practicality, and respect for what the theory actually delivers. It accepts uncertainty at the level of meaning while insisting on precision at the level of prediction. For many working physicists, that balance has been enough. Not because it resolves every question, but because it allows the work to continue without pretending that unanswered questions have already been settled. In the quiet space between certainty and curiosity, the Copenhagen interpretation has endured, not as a final answer, but as a workable way forward. One response to the unease surrounding measurement is to remove the problem altogether. Instead of asking why one outcome appears and the others disappear, this approach asks a different question. What if none of the outcomes vanish at all? This idea forms the heart of what is known as the many worlds interpretation. At first hearing, the name alone can pull the imagination towards science fiction. Endless universes, dramatic splits, copies of reality branching at every decision. These images are vivid, but they're not the best way to understand what the interpretation is actually proposing. At its core, the many worlds interpretation is surprisingly conservative. It does not add new rules to quantum mechanics. It does not introduce special moments of collapse. It takes the mathematics exactly as it stands and follows it to its logical conclusion, even when that conclusion feels uncomfortable. The key move is simple. The wave function never collapses. According to the equations of quantum mechanics, the wave function evolves smoothly and deterministically over time. There is no term in the mathematics that explicitly describes a collapse. That idea was introduced later as a way of connecting probabilities to definite outcomes. The many worlds interpretation asks what happens if that extra step is removed. If the wave function always evolves according to the same rules, then every possible outcome allowed by the mathematics continues to exist. When a measurement occurs, the system does not choose one result. Instead, the combined system of observer, apparatus, and environment becomes entangled in such a way that different outcomes no longer interfere with one another. The result is branching. Each branch contains a consistent version of events, with a definite outcome recorded. Within any given branch, the world appears perfectly ordinary. Measurements have single results. Cats are either alive or dead. Instruments show clear readings. Nothing feels fuzzy or unresolved. What has changed is not the experience within a branch, but the structure of the overall description. Branching is not something added by hand. It emerges naturally from the mathematics when systems interact and entangle. Once different outcomes become correlated with different states of the environment, they effectively decouple. They stop influencing one another. From that point on, each branch evolves independently. There is no moment where reality splits with a flash or a sound. There is no cosmic fork in the road announcing itself. Branching is quiet, continuous, and constant, happening whenever interactions distribute quantum information into the environment. This interpretation removes the need for collapse entirely. There is no sudden reduction of possibilities. There is no special role for measurement. The same rules apply at all times, to all systems, without exception. For many physicists, this simplicity is appealing. The cost of this simplicity is conceptual rather than mathematical. Accepting that all outcomes persist requires a willingness to let go of the idea that there is only one unfolding history. Instead, there is a vast structure of histories, each internally consistent, each following naturally from the same underlying laws. It is important to be clear about what this does and does not imply. The many worlds interpretation does not suggest that new universes are being created from nothing. It does not require extra dimensions or exotic physics beyond quantum mechanics itself. It describes a single universal wave function that contains many non-interacting branches. These branches are not accessible to one another. Once they separate, there is no communication, no influence, no way to move between them. From within any one branch, the others might as well not exist. This is why the interpretation does not lead to practical contradictions. It makes the same experimental predictions as other interpretations. No test performed so far can distinguish many worlds from collapse-based approaches. The difference lies entirely in how the mathematics is understood. Critics often ask where probability fits into this picture. If all outcomes occur, what does it mean to say that one is more likely than another? The answer is subtle. Probability in this context is not about whether an outcome happens, but about how much weight a given branch carries within the overall wave function. Branches are not all equal. Some have much greater mathematical weight than others, corresponding to outcomes that appear more frequently in repeated experiments. From the perspective of an observer within a branch, outcomes appear random, but the statistics across many trials match the probabilities predicted by quantum mechanics. The interpretation preserves everything that works about the theory, while reframing what probability means. Another common worry is that the idea feels extravagant. Too many worlds, too much reality. But extravagance is a matter of perspective. Adding a special collapse rule to the equations can also be seen as extravagant. The many worlds interpretation avoids that by refusing to modify the mathematics at all. It accepts the consequences instead. The interpretation also offers a clean resolution to the measurement problem. There is no need to explain how or when collapse occurs, because it never does. There is no special boundary between quantum and classical behaviour. Large systems appear classical because their branches rapidly become isolated from one another through interaction with the environment. What looks like collapse is simply branching that has become irreversible. The unease many people feel toward this picture often comes from trying to imagine it too literally. It is not necessary to picture countless visible copies of the universe fanning out at every moment. The mathematics does not require that image. What it requires is acceptance that the full description of reality is larger than any single experienced history. From inside one branch, the world feels singular and complete. Memory, identity, and experience all remain intact. There is no sense of duplication or loss. The interpretation does not deny experience. It explains why experience feels the way it does. Many worlds is not an attempt to turn physics into speculative fiction. It is an attempt to take the existing theory seriously without adding extra rules to make it more comfortable. Whether one finds that compelling or unsettling is a matter of taste rather than experiment. Some physicists appreciate its mathematical honesty. Others find its implications too heavy to carry. Both reactions are understandable. What matters is that the interpretation demonstrates something important about quantum mechanics. The strangeness does not come from adding imaginative stories. It is already present in the equations. Different interpretations simply choose different ways to live with it. The many worlds interpretation chooses to keep the mathematics untouched and let reality be larger than intuition expects. In doing so, it replaces collapse with continuity and singular outcomes with a branching structure that remains hidden, not because it is forbidden, but because each branch is complete on its own. All outcomes occur, no collapse is required. For a long time, it was natural to think of particles as the most basic ingredients of reality. Little points of matter moving through space, colliding, bouncing, and occasionally sticking together. This picture worked well enough for everyday experience and even carried physics a long way into the microscopic world. Electrons, protons, neutrons, and photons became the cast of characters, each treated as a tiny object with its own properties and behaviour. Quantum field theory quietly turns that picture inside out. Instead of beginning with particles, it begins with fields, not as optional additions or mathematical conveniences, but as the underlying fabric of reality itself. In this view, particles are no longer the foundation. They are events, temporary excitations that appear when fields are disturbed in particular ways. This shift can feel subtle at first, but it changes everything. A field in this context is something that exists everywhere, even in places where nothing seems to be happening. It assigns a value or a potential for activity to every point in space. Some fields describe electrical effects, others magnetic behaviour, others still are responsible for mass or interaction strength. Space is not an empty container holding particles. Space is saturated with fields. When nothing disturbs a field, it sits quietly in its lowest energy state. When something does disturb it, the field responds, and that response can appear as a particle. In this way, a particle is not a tiny object travelling through an empty void. It is a ripple, a localized vibration of an underlying field, carrying energy and momentum as it moves. Much like a wave on the surface of water, it has a presence and an effect, but it is inseparable from the medium that supports it. This analogy is not perfect, but it captures the spirit of the idea. There is no electron without the electron field, no photon without the electromagnetic field. The particle is what the field is doing at that moment. Quantum field theory brings together quantum mechanics and special relativity into a single framework. It treats fields quantum mechanically, allowing them to fluctuate, interact, and exchange energy in discrete ways. The mathematics can become intricate, but the conceptual core is surprisingly simple. Fields are fundamental, particles are secondary. This helps resolve several puzzles that arise when particles are treated as the deepest layer of reality. For example, particles can be created and destroyed. They appear in interactions and vanish again without leaving debris behind. If particles were truly fundamental objects, this behaviour would be difficult to reconcile. If they are excitations of fields, creation and destruction become natural. Energy goes into a field. A ripple appears. Energy leaves, and the ripple fades. The same reasoning applies to forces. In quantum field theory, forces are not mysterious influences acting at a distance. They arise from interactions between fields. When two charged particles repel or attract, what is really happening is an exchange of disturbances in the electromagnetic field. The language of force is a convenient summary of deeper field behaviour. This framework also reshapes how solidity itself is understood. At first glance, solid objects feel firm, impenetrable, and stable. Tables do not collapse when touched. Walls resist motion. This seems to suggest that matter is made of rigid building blocks stacked together. Quantum field theory offers a different explanation. Solidity emerges from interaction. The atoms in a solid are held in place by electromagnetic interactions between electrons and nuclei. These interactions are described by fields responding to one another. When a hand presses against a table, the fields associated with the atoms in the hand interact with the fields associated with the atoms in the table. The resistance felt is not the collision of hard objects, but the result of fields strongly opposing further overlap. The sensation of solidity is a consequence of balance, not rigidity. On very small scales, most of what makes up an atom is empty space. The nucleus occupies a tiny region at the centre, while electrons exist as probability clouds around it. Yet when many atoms come together, their fields arrange themselves into stable patterns that resist disruption. What feels solid is a collective effect, arising from countless field interactions operating together. This perspective helps explain why matter can be both sturdy and fragile. Fields can form stable configurations, but they can also be rearranged. Change the arrangement, and the properties of matter change with it. Solids melt, metals conduct, insulators resist. All of this flows from how fields are organized, not from the intrinsic hardness of particles. Quantum field theory also provides a natural way to understand why different particles exist at all. Each type of particle corresponds to a different field, with its own properties and behavior. Some fields allow heavy excitations, others only light ones. Some interact strongly, others barely at all. The diversity of particles reflects the diversity of fields. In this picture, the universe resembles a layered ocean rather than a pile of objects. The surface may appear calm or busy depending on conditions, but beneath it lies a continuous medium capable of supporting many kinds of motion. What we call particles are the visible signs of that motion. This does not mean that particles are illusions. They're real, measurable, and useful concepts. It means that they are not the deepest layer. Treating them as fundamental works in many situations, just as treating waves as objects can be useful when studying water. But when pushed too far, that picture breaks down. Fields endure where particles come and go. One of the quiet strengths of quantum field theory is that it unifies many ideas that once seemed separate. Forces and particles become two sides of the same coin. Creation and annihilation become natural processes. Even the vacuum, as seen earlier, takes on a richer character, shaped by the fields that fill space even in their lowest energy states. From this viewpoint, the universe is not made of things sitting in space. It is made of activity occurring in fields that define what space itself can do. Matter, light and interaction all arise from this deeper layer, emerging when conditions allow. This does not strip the world of familiarity. Tables remain solid. Light still shines. Particles still register in detectors. What changes is the explanation beneath those experiences. Solidity is no longer a primitive fact, it is a result. Quantum field theory does not ask that intuition be abandoned entirely. It asks that it be refined. The world feels like it is built from objects because, at large scales, field excitations behave in stable, object-like ways. At smaller scales, the continuity underneath becomes hard to ignore. Fields beneath everything do not make reality less real. They make it more coherent. They provide a common foundation from which particles, forces, and even empty space itself can be understood as variations on a single theme. The universe, at its deepest level, is not a collection of tiny beads. It is a set of fields, always present, quietly shaping everything that can appear. Once fields are accepted as the deeper layer beneath particles, the question naturally shifts from what things are made of to how many kinds of excitations exist and how they behave. Over the past century, physicists have assembled a remarkably successful catalogue of these excitations, a framework known as the Standard Model. It is not a theory of everything, and it does not claim to be complete, but within its limits it works with extraordinary precision. The Standard Model is best thought of as an inventory, a carefully organised list of the known fundamental particles and the rules that govern how they interact. It does not explain why these particular particles exist, or why they have the properties they do. It simply describes them, accurately enough that experiments and predictions line up to an almost unsettling degree. At the heart of this inventory are two broad families of matter particles known as quarks and leptons. These are not objects in the everyday sense, but stable patterns of excitation in their respective fields. They do not break down into smaller pieces, at least as far as current experiments can tell. When matter is analysed at the deepest level available, these are the pieces that remain. Quarks are the constituents of protons and neutrons, and therefore of atomic nuclei. They never appear in isolation. They are permanently bound together by a powerful interaction that becomes stronger the more one tries to pull them apart. This behaviour is so counterintuitive that it took decades to accept. Instead of weakening with distance, the force between quarks intensifies, ensuring that they remain confined inside larger structures. There are several types of quarks, differing in mass and other properties, but they all follow the same basic rule. They combine in specific ways to form composite particles, and those composites make up the familiar matter found in the universe. Every proton in every atom owes its existence to this quiet but relentless rule. Leptons form the second family. The most familiar member is the electron, the particle responsible for electricity, chemistry, and much of what makes matter behave the way it does. Unlike quarks, leptons can exist on their own. They do not experience the same confining force, which is why electrons can move freely through materials and form currents. Alongside the electron are heavier relatives that behave similarly, but decay quickly into lighter forms. These heavier leptons rarely play a role in everyday matter, but they appear in high-energy experiments and cosmic processes, reminding physicists that the particle list is richer than daily experience suggests. Then there are the neutrinos, members of the lepton family that are famously elusive. They interact so weakly with other matter that vast numbers pass through the Earth every second without leaving a trace. For a long time they were assumed to have no mass at all. It later became clear that they do have mass, just extremely little, a discovery that quietly signalled one of the ways the Standard Model was incomplete. Matter particles alone are not enough to describe the universe. Interactions require mediators, and the Standard Model includes these as well. They are often called force carriers, though once again it is more accurate to think of them as excitations of fields that enable interactions to occur. The electromagnetic interaction is carried by photons, excitations of the electromagnetic field. They are responsible for light, radio waves, and the forces that bind atoms together. Their behaviour is so familiar that it is easy to forget how deeply they shape reality. Without them, chemistry would vanish, and matter would lose its structure. The strong interaction, which binds quarks together, is carried by particles that operate only at extremely short ranges. Their effects are confined to the interior of atomic nuclei, but within that tiny domain they dominate completely. Without this interaction, protons and neutrons would not hold together, and atoms would fall apart before they ever formed. The weak interaction governs certain kinds of decay and transformation. It allows particles to change identity, enabling processes that power stars and drive radioactive decay. Its effects are subtle in daily life, but without it, the universe would be a very different place. Together, these interactions form a tightly woven system. The mathematics describing them has been tested repeatedly and refined with increasing precision. Experiments have confirmed predictions to many decimal places. In terms of accuracy, the Standard Model is one of the most successful frameworks ever constructed. And yet, it is clearly unfinished. One major piece is missing entirely. Gravity does not fit comfortably into the Standard Model. While it governs the motion of planets and the structure of galaxies, it is extraordinarily weak at the particle level. Attempts to describe gravity in the same quantum language as the other forces have not yet produced a complete and consistent picture. There are other gaps as well. The Standard Model does not explain dark matter, the unseen mass that shapes galaxies and clusters. It does not account for dark energy, the influence driving the expansion of the universe. It does not explain why particles have the masses they do, only how those masses behave once assigned. Even within its own structure, the model contains numbers that must be measured rather than derived. They are put in by hand, not predicted from deeper principles. This has led to a recurring sense that the model, for all its success, is more like a map than a final explanation. A very good map. One that tells where things are and how they connect, but not why the landscape has the shape it does. There is gentle humour to be found in this situation. The Standard Model is often described as a triumph, and it is. But it is also a reminder that even the most accurate theories can feel slightly provisional. Like a beautifully furnished house with a few locked rooms and an unfinished extension, it works perfectly well for daily life, while quietly hinting that more is yet to come. Physicists are comfortable with this state of affairs. The model does not pretend to answer every question. It earns its place by matching reality where it applies, not by claiming completeness. Its limitations are not hidden, they are studied. In practice, this balance has been productive. By knowing exactly where the model succeeds and where it fails, physicists can design experiments that probe its boundaries. Every confirmed prediction strengthens confidence. Every discrepancy offers a clue. The known pieces of the universe, as described by the Standard Model, fit together with remarkable precision. Quarks form nuclei. Electrons shape chemistry. Force carriers mediate interactions. Fields provide the foundation beneath it all. It is an elegant structure, even if it is not the final one. What the model ultimately teaches is a kind of intellectual patience. Understanding can be deep and still incomplete. A theory can be extraordinarily accurate and still provisional. Progress does not require final answers, only better ones. The Standard Model tells a clear story about what is known. It leaves space, deliberately and honestly, for what is not. When physicists speak quietly among themselves about success, there is one theory that almost always earns a pause of respect. Not because it is simple, and not because it is philosophically satisfying, but because it works with a level of accuracy that borders on the absurd. This theory is quantum electrodynamics, often shortened to QED, and it describes how light and matter interact. At its heart, quantum electrodynamics is concerned with a very familiar relationship: how charged particles, such as electrons, respond to electromagnetic fields, and how light itself participates in those interactions. Every glow, reflection, spark, and electrical current ultimately traces back to this framework. It governs how atoms hold together, how chemistry unfolds, and how energy moves from place to place in the form of radiation. What makes QED remarkable is not just that it explains these things, but how precisely it does so. When predictions made by quantum electrodynamics are compared with experimental results, the agreement is astonishing. The theory does not merely get the general shape right, it matches reality down to a level of detail so fine that it strains intuition. Measurements and calculations line up with a precision that feels almost excessive, as if the universe were double-checking its work. This accuracy did not appear by accident. QED emerged from decades of careful refinement, driven by the need to reconcile quantum mechanics with the demands of special relativity. Early attempts ran into serious problems. Calculations produced infinities that made no physical sense. Quantities that should have been finite instead blew up without limit. Rather than abandoning the theory, physicists learned how to tame these divergences through a process known as renormalization. The details are technical, but the underlying idea is gentle. Instead of pretending that particles are perfectly isolated points, the theory acknowledges that they are always interacting with surrounding fields. Once this interaction is handled carefully, the infinities cancel in just the right way, leaving behind meaningful, testable predictions. The fact that this procedure works at all is one of the quiet wonders of modern physics. Within quantum electrodynamics, interactions between light and matter are described as exchanges between fields. An electron does not emit or absorb light as a little object tossing particles back and forth. Instead, disturbances in the electron field and the electromagnetic field influence one another, producing outcomes that appear as emission, absorption, or scattering. This picture allows the theory to account for an enormous range of phenomena. It explains why atoms emit light at specific frequencies. It explains why electrons repel one another. It explains how light bends around obstacles and how materials become transparent or opaque. All of these behaviours arise from the same underlying rules. To make these calculations manageable, physicists often use diagrams introduced by Richard Feynman. These diagrams are not pictures of what actually happens in space and time. They are visual bookkeeping tools that help organize calculations. Lines and vertices represent terms in an equation, not literal paths taken by particles. Even so, the diagrams have become iconic, partly because they give a human scale to an otherwise abstract process. They allow complex interactions to be broken down into simpler components, each contributing a small piece to the final result. When all those pieces are added together, the answer matches experiment with extraordinary fidelity. And yet, for all this success, quantum electrodynamics carries a quiet tension. The theory is unmatched in its predictive power, but it does not necessarily offer a satisfying picture of what is really happening. It tells what will occur, and with stunning accuracy, but it is less forthcoming about why the world is organized this way rather than another. The mathematics works. The interpretation remains open. This gap between accuracy and understanding is one of the defining features of modern physics. QED can calculate outcomes to an almost ridiculous number of decimal places, yet the deeper meaning of its components is still debated. Are the fields real, or are they calculational devices? Are particles best thought of as excitations or as convenient labels for interactions? Different interpretations answer differently, and none are ruled out by experiment. There is a gentle irony here. The most accurate theory ever built is also one that resists simple storytelling. It is tempting to assume that precision brings clarity, that a theory which predicts so well must also reveal the ultimate nature of reality. Quantum electrodynamics reminds us that these are separate achievements. A tool can be exquisitely accurate without being conceptually transparent. Physicists have learned to live with this distinction. In practice, understanding how to calculate correctly often matters more than having a perfectly intuitive picture. Devices are built, experiments are designed, technologies function. The theory earns its trust through results. At the same time, the unease never entirely disappears. There remains a sense that QED, for all its brilliance, is part of a larger story rather than its conclusion. It fits beautifully within the standard model, but it does not explain why the model has the structure it does. It does not tell why the strengths of interactions take the values they do. It does not resolve how gravity should join the framework. Accuracy, it turns out, is not the same as completeness. There is also something quietly humbling in the success of quantum electrodynamics. It suggests that the universe follows rules that are internally consistent in ways humans can uncover, even if the reasons behind those rules remain elusive. The match between calculation and observation feels less like domination and more like alignment. Nature is not being forced to comply. It already does. For those who work with a theory daily, this creates a particular mindset: confidence in the calculations, paired with caution about interpretation. A willingness to accept that a framework can be both deeply successful and philosophically unfinished. Quantum electrodynamics stands as a reminder that science does not always advance by replacing imperfect theories with perfect ones. Sometimes it advances by finding tools that work so well they reveal the limits of what explanation itself might mean. Light and matter continue to interact exactly as QED predicts. Electrons behave, photons scatter, measurements agree. The theory does its job with quiet, relentless precision. Whether it tells the full story of what light and matter truly are remains an open question. And perhaps that is part of its lesson. Computers feel decisive. A calculation is performed, an answer appears, and the machine moves on. Beneath that smooth surface lies a simple logic built from clear alternatives: on or off, yes or no, one state or another. This structure has served technology extraordinarily well, carrying it from room-sized machines to devices that fit in a pocket. Quantum computing begins by questioning that simplicity, not because it is wrong, but because it is incomplete at very small scales. At the heart of an ordinary computer is the bit, a unit of information that exists in one of two states. A bit is either 0 or 1. Every image, sound, and calculation is built by combining vast numbers of these simple choices. The power of classical computing comes from speed and scale, from performing many operations very quickly and storing enormous amounts of information reliably. A quantum computer uses a different kind of unit, known as a qubit. Like a bit, a qubit can represent 0 or 1. Unlike a bit, it is not limited to choosing immediately. A qubit can exist in a superposition, carrying the possibility of 0 and 1 at the same time, weighted in specific ways. This does not mean the qubit is confused. It means it is described by a broader set of possibilities until interaction forces a specific outcome. When multiple qubits are combined, their possibilities do not merely add, they intertwine. The system can explore many configurations at once, not by racing through them one after another, but by allowing them to coexist within a single evolving state. This behaviour is often described as parallelism. though that word can be misleading if taken too literally. A quantum computer is not trying every possible answer simultaneously in the way a group of classical computers might. It is shaping a landscape of possibilities and guiding it so that certain outcomes become more likely when measured. This guidance is subtle and fragile. Quantum states are easily disturbed. Interaction with the environment, even in small amounts, can disrupt the delicate superpositions and correlations that give quantum computation its power. Heat, vibration, stray electromagnetic fields, and random noise all work against coherence. As a result, building and maintaining quantum computers is extraordinarily challenging. The qubits themselves can take many forms. They may be realized using trapped ions, tiny currents in superconducting circuits, or other carefully controlled quantum systems. Regardless of the physical implementation, the underlying challenge remains the same. The system must be isolated enough to preserve quantum behaviour, yet accessible enough to be manipulated and measured. This balance is difficult to achieve. Because of these constraints, quantum computers are not general replacements for classical machines. They excel at certain kinds of problems and offer little advantage for others. Tasks involving large amounts of straightforward arithmetic or everyday data processing are usually better handled by classical computers, which are faster, more stable, and far easier to scale. Quantum computing shines in more specific domains. Certain problems involving optimization, simulation of quantum systems, and particular kinds of pattern searching can benefit from quantum approaches. These are problems where the structure of the task aligns naturally with the way quantum states evolve. When that alignment exists, a quantum computer can reach solutions in ways that would be impractical for classical machines. Even here, expectations must be tempered. Much of the popular conversation surrounding quantum computing leans toward dramatic futures and revolutionary change. Machines that break all encryption overnight. Devices that instantly solve any problem. These narratives make for exciting headlines, but they oversimplify both the promise and the limits of the technology. In reality, quantum computers are specialized tools. They do not think faster in every way. They think differently. Their strength lies in exploiting superposition and entanglement to reshape problem spaces, not in brute force calculation. Designing algorithms that take advantage of this behavior is itself a complex task, requiring deep understanding of both quantum physics and the structure of the problem being addressed. Progress in this field has been steady rather than explosive. Small quantum processors exist and can perform controlled experiments. They demonstrate principles rather than universal capability. Errors remain a major obstacle. Correcting those errors requires additional qubits, which increases complexity and introduces new challenges. The path forward involves incremental improvement rather than sudden transformation. There is also an important philosophical shift embedded in quantum computing. It reflects a move away from thinking of computation as a sequence of definite steps toward viewing it as an evolution of probabilities. The answer emerges not because every wrong path is eliminated, but because the right path is amplified. This way of thinking mirrors the quantum world itself. Possibilities are allowed to exist together. Interference shapes outcomes. Certainty appears only at the end. That parallel is not accidental. Quantum computing does not impose a new way of thinking onto physics. It borrows one that physics has been using all along. The technology works best when it respects the grain of the quantum world rather than trying to force it into classical molds. For now, classical and quantum computing coexist comfortably. Classical machines handle the vast majority of tasks efficiently and reliably. Quantum devices explore niches where their unusual properties offer genuine advantages. The two approaches complement rather than replace one another. There is a quiet maturity in recognizing this balance. Quantum computing is not a shortcut to intelligence, nor a replacement for human thought. It is a specialized extension of computational capability, shaped by the same quantum rules that govern atoms, light, and matter. Its progress depends not on hype, but on careful engineering, realistic expectations, and continued refinement. When technology thinks differently, it does so by aligning with the deeper structure of reality, not by escaping it. The promise of quantum computing lies not in rewriting the future overnight, but in opening new ways to approach problems that were previously out of reach, slowly, deliberately, and with an awareness of both power and limitation. In that sense, it is less a revolution and more a conversation between physics and technology, one that is still learning how to listen. At first, probability feels like a compromise, a stand-in for ignorance. When something cannot be predicted exactly, it is tempting to assume that the missing certainty is only temporary, that with better tools, better measurements, or more information, the randomness would fade away and a clear cause would emerge. This expectation runs deep, shaped by centuries of classical thinking, in which uncertainty usually meant incomplete knowledge rather than an incomplete world. Quantum physics gently challenges that assumption. At the smallest scales, probability does not behave like placeholder for what is not yet known. It behaves like a fundamental feature of how reality unfolds. The theory does not merely use probabilities as a practical shortcut. It builds them into the structure of its predictions. Even when everything that can be known is known, outcomes remain probabilistic. This is not because the universe is careless. It is because the universe appears to be organized this way. In classical physics, randomness often signals ignorance. Toss a coin, and the result feels random only because tracking every air current, muscle movement, and surface interaction is impractical. In principle, the outcome is determined. With perfect information, the future could be calculated exactly. Probability enters the picture only because perfect information is unavailable. Quantum randomness is different. When a quantum system is prepared in the same way again and again, and measured under identical conditions, the results vary. Not because something was missed, but because the theory itself assigns only probabilities to outcomes. The same preparation leads to a distribution of results, not a single inevitable one. Nothing is being hidden. There is no deeper list of facts waiting to be uncovered that would restore certainty. The probabilities are not masks, they are the content. This distinction matters because it reshapes the relationship between prediction and explanation. Quantum physics does not fail to predict outcomes. It predicts them in a different way. It predicts how often each outcome will occur, not which one will appear next. Over many trials, the statistics settle into stable patterns. Those patterns are as reliable as any law in classical physics. What changes is the level at which certainty applies. The universe, in this view, is not a machine ticking forward along a single track. It is a process that unfolds by exploring possibilities and selecting outcomes according to fixed probabilities. The rules governing those probabilities are precise. The individual events are not. This idea can feel unsettling at first, especially to minds trained to associate explanation with inevitability. There is comfort in believing that everything happens for a definite reason, that each event is the only one that could have occurred given the state of the world before it. Quantum physics loosens that grip. Some things happen without being uniquely determined. That does not mean they happen without cause. The probabilities themselves arise from the structure of the system and the conditions under which it evolves. Change the setup, and the probabilities change with it. The randomness is constrained, shaped, and lawful. A useful way to think about this is to imagine a landscape rather than a path. Classical physics traces a line through terrain. Given a starting point and a direction, the route is fixed. Quantum physics describes a terrain of hills and valleys, where motion spreads across many routes at once, guided by slopes that favour some outcomes over others. The shape of the landscape matters more than the specific trail taken. Within this landscape, individual events feel surprising, but the overall flow remains predictable. Just as weather cannot be predicted drop by drop but can be forecast in patterns, quantum events resist exact prediction while obeying stable statistical laws. This perspective reframes uncertainty as something to work with rather than something to eliminate. It also opens a different kind of philosophical space. If probability is fundamental, then the universe is not a finished object with every detail fixed in advance. It is an ongoing process, a continuous negotiation between what is possible and what becomes actual. Reality in this sense is not a thing, it is an activity. Each interaction narrows possibilities, each outcome contributes to the next set of conditions. The world unfolds moment by moment, not by revealing a pre-written script, but by writing itself as it goes, within the constraints of physical law. There can be comfort in this view. Certainty can be heavy. A universe where everything is fixed from the beginning leaves little room for novelty. Universe built on probability allows for variation, emergence, and genuine change. The future is shaped by the past but not locked by it. This does not mean that anything can happen. The probabilities are not uniform. Some outcomes are overwhelmingly likely. Others are so rare that they may never occur within the lifetime of the universe. Structure and regularity still dominate. The world is not a roll of dice without rules, but it is a roll of dice with rules. Accepting this can soften the demand for absolute explanations. Instead of asking why this exact event occurred rather than another, quantum physics encourages attention to patterns, why these outcomes are favoured, why these probabilities arise, why the landscape has the shape it does. In this way, understanding shifts from seeking inevitability to recognizing constraint. There is also a quiet honesty in probability. It does not pretend to know more than it can justify. It does not invent hidden mechanisms to preserve certainty when none is required by evidence. It states plainly what can be predicted and what cannot, and it does so without apology. This honesty has practical benefits. Technologies built on quantum principles rely on probabilistic behaviour. Lasers, semiconductors, and imaging techniques all exploit predictable randomness rather than fighting it. Stability emerges not by eliminating uncertainty, but by harnessing it. At a deeper level, probability invites a different relationship with the unknown. Uncertainty becomes something to be navigated rather than feared. It marks the boundary between what can be specified and what must be allowed to vary. This is not ignorance, it is openness. The idea that reality is fundamentally probabilistic does not strip it of meaning. If anything, it enriches it. It suggests that the universe is not merely replaying a static design, but actively participating in its own unfolding. Each event contributes something new, however small, to the ongoing pattern. Even identity takes on a softer edge in this view. Objects persist not because they are frozen in place, but because probabilities overwhelmingly favour continuity. Change is possible, but stability is likely. What feels solid is not absolute. It is statistically reinforced. This perspective aligns naturally with the quantum picture developed throughout this journey. Superposition allows multiple possibilities to coexist. Measurement narrows them. Entanglement preserves relationships. Fields provide structure. Probability weaves through all of it, not as an afterthought, but as the thread holding it together. Randomness in this sense is not the opposite of order. It is part of how order expresses itself at the smallest scales. The universe made of chances is not careless or chaotic. It is precise about the range of what can happen. even if it remains undecided about which option will occur next. That undecidedness is not a flaw. It is a feature that allows richness, complexity, and novelty to arise. Reality does not march forward along a single predetermined line. It unfolds across a field of possibilities, selecting outcomes according to rules that are firm but not rigid. Seen this way, uncertainty becomes less threatening. It becomes a sign that the universe is not finished, not frozen, not closed. It is active, responsive, and open within limits that keep it coherent. A universe made of chances is not a universe without meaning. It is a universe where meaning emerges through process, where patterns matter more than individual outcomes, and where the future is shaped but not sealed. In that openness, there is room to breathe, and perhaps, quietly, room to rest. As the journey through quantum ideas slows, there is no need to tie everything into a neat conclusion. Quantum physics does not reward certainty in that way. It offers something quieter and perhaps more lasting. Again and again, the deeper the investigation goes, the less the universe resembles a finished object. What appears instead is a process, a world that unfolds through interaction, probability, and relationship. A reality that resists being pinned down completely, not because it is chaotic, but because it is subtle. There is humility in that realization, the comforting belief that everything can be fully known, fully predicted, and fully explained gives way to something softer, not ignorance, but restraint, an understanding that some questions do not have final answers, and that this is not a failure of thinking, but a feature of the world itself. Quantum physics invites that humility without demanding surrender. It shows that precise knowledge and uncertainty can coexist, that prediction does not require certainty, that understanding can deepen even when mystery remains intact. Letting go of certainty does not mean letting go of meaning. It means releasing the demand that the universe must behave in ways that feel familiar. It means allowing reality to be stranger, quieter, and more open than expectation once allowed. There is wonder in that openness. Not the loud wonder of spectacle or shock, but the steady kind that comes from recognizing how much care the universe seems to take in balancing possibility and constraint. Nothing is entirely free, nothing is entirely fixed. Between those extremes, structure emerges. The most remarkable thing may not be any single quantum phenomenon, but the attitude the theory encourages. A willingness to explore without insisting on closure. A patience with unanswered questions. A respect for what can be known, paired with an acceptance of what cannot. Curiosity itself becomes the quiet constant. Every experiment, every calculation, every careful question asked about the nature of reality arises from that same impulse. Not to conquer the unknown, but to approach it honestly. To listen closely to what the universe is willing to reveal, and to stop where it remains silent. There is something restful in that stance. The pressure to have final answers fades. The need to resolve every paradox softens. What remains is a sense of participation in an ongoing conversation, one that did not begin with any single observer, and will not end with one either. Quantum physics does not offer a place to stand outside reality and see it whole. It offers a way to stand within it, attentive, curious, and aware of limits. And perhaps that is enough. To rest with the unknown, to let questions remain open, to feel gratitude not for certainty but for the ability to wonder at all.